Assalamu alaikum. We know whenever electric current flows through a conductor, it produces magnetic field around it. In this video, we are going to get the expression for magnetic field due to a current carrying wire of infinite length using Ampere circuital law. Before getting into the problem, let me tell you what is Ampere circuital law. It says that line integral of a magnetic field over a closed loop is equal to mu naught times the current enclosed by the loop. Here I is nothing but the net current enclosed by the loop. Here C is the enclosed loop. Now let's go ahead. Let me draw the wire, diagram of the wire which carries current. This is a uniform wire of infinite length. See, when I say uniform wire, that means the thickness of the wire remains same throughout the length. Here the current flowing through this one is nothing but I, represented by this direction. It flows upward. Clear? Now, whenever we apply Ampere circuital law, we take a Ampere loop. Okay, we take a closed loop within which we place the current carrying conductor. We call that loop as Ampere loop. So in that way, Ampere circuital law appears similar to Gauss law in electrostatics. In Gauss law, we use the Gaussian surface. Here, we use Ampere loop, within which we take the current carrying conductor. Okay. Now, I consider this one as Ampere loop, which is in the form of a circle which surrounds the current carrying conductor. Then a point is taken here named as O, which acts as the center of this circle, which is nothing but Ampere loop. Then I draw here a line here which touches the circle. So it is nothing but the radius of this circle, represented by letter R. Clear? After that, I draw a tangent here. We know tangent. What is a tangent? Tangent is nothing but a line that goes touching a curve or a circle. I take this point as A, and this tangent is nothing but it provides us the magnetic field due to this line element. Due to the line element dl along the tangent. Okay, this line element along the tangent, or it is along the Ampere loop, represented by the tangent. I repeat, here dl is the line element along the Ampere loop, represented by this tangent. Clear? Okay, that way we can proceed to get the value of B. Now write this equation here, which is nothing but Ampere circuital law. Now here B vector actually represents the magnetic field produced by this current carrying conductor, and dl is the line element along this Ampere loop. it is so, the angle between B and DL is taken as a theta, which is found to be 0 according to the diagram. Okay, if DL acts along B, then the angle between them will be 0 only. If it is so, and here we know, let's see, these two vectors are in a dot product. We know very well, if two vectors are in dot product, if we have A vector dot B vector, then this can be written as AB cos theta. The similar way, here, this product can be represented as BDL cos theta goes to mu naught I. Then in the place of cos theta, I write its value. There's nothing but cos of 0. So, close integral of BDL cos of 0 equals to mu naught I. Okay. Here mu naught is nothing but permeability of free space. Remember that. And I is the current. And we know cos of 0 is nothing but 1. So that way, this becomes equal to close integral of BDL multiplied with 1 equals to mu naught I. So this can be written as closed integral of BDL equals to mu naught I. Fine. Here, I forgot to mention C here. This C is closed loop. Now, I told you earlier, the thickness of this current carrying wire remains same throughout the length. So the magnetic field produced by this one also remains same throughout the length. So if it is so, then magnetic field is uniform. That means it is a constant. So B is constant. In that way, if it is constant, then we cannot integrate it. So it is taken out. This equation can be written as B of DL equals to mu naught I. Okay. Now, this closed integral is represented this way. How do I write this? Now, see how I write it. I write it as line integral over DL with lower limit as 0 and upper limit as 2 pi r. So here 2 pi r is nothing but the circumference of this circle. Okay. It provides the total length of this loop. So I have removed a closed integral. In the place of that, I have written line integral. Fine. Because here I have given the lower and upper limit. Understand? Then I go ahead, write this mu naught I. Now I am going to integrate this. Before doing so, if I integrate dl, let me tell you what I will get. Here we know this. Integral of dx is nothing but x. In the similar way, if I integrate dl, what I'll get? I'll get a L. Got it? Got it? Let me write this one here. Here B is mentioned as such. Then integral of dl becomes L. Then the upper limit and lower limit and upper limit are mentioned here in this way. I hope you have understood. After that, this portion, this That is written here as such. Now, after doing this, look at this carefully. What I do now, I am going to substitute the value of L. Now, the upper limit is represented in the place of L. Now, in the place of L, I write the upper limit. That is 2 pi r minus. Then, in the place of L, I substitute the lower limit. That is 0. So, it is equal to mu naught I. After that, becomes B multiplied with 2 pi r. Then we have 0. So, if I multiply B with 0, I get a 0. So, you have to write that here. This is equal to mu naught I. Here, my aim is to get the value of B. So, I keep B on the left hand side. Then I take a 2 pi r to the right hand side. What I'll get? Mu naught I upon 2 pi r. This is the expression for magnetic field due to a current carrying infinite long wire. Okay. In vector form, this can be written as, see, how do I write this one in vector form? Vector form is written in this manner. B vector. Now, mu naught I upon 2 pi r. Then here I include a unit vector. This is n cap. Here n cap is the unit vector which acts along the tangent. So this acts along the tangent. This is n cap. I repeat, here n cap is nothing but the unit vector acting along the tangent. Before I conclude, I just box this for better visibility. I hope the video is useful. If you have any kind of doubt related to the topic, can you put a question in the comment section. Thanks for watching.